Right now, the universe is stretching apart at two different speeds at once, and the gap between them refuses to close. Astronomers at Caltech, at Harvard, at the Space Telescope Science Institute, they have measured it more than 70 different ways. It will not agree with itself. Every method should point to the same number. None of them do. And buried inside that gap is a possibility so unsettling, some physicists don't want to say it out loud. But here's what nobody is telling you: this isn't a rounding error, it's growing. And it might mean the universe is lying to us about its own age. Here's what you need to know first. Scientists call it the Hubble Constant, a number that tells you how fast the universe is expanding everywhere all the time. Name any galaxy. Measure how fast it's flying away from us. That number should be the same no matter how you check it. There are two ways to check it. One uses the leftover light from the Big Bang. The oldest light there is over 13 billion years old. The other uses nearby stars, ones we can actually see pulse and flicker in galaxies close to home. Both methods are considered gold standard. Both have won Nobel Prizes. And in the 1990s, when the instruments were rougher, both landed close enough to shrug off. Nobody worried. Yet. Then the instruments got better, sharper, more precise. And that's when it happened. The two numbers didn't move closer together, they moved apart. The early universe method says the expansion rate is about 67. The nearby star method says 73, 6 points apart. Doesn't sound like much. In cosmology, it's an earthquake. And the more precise our tools become, the wider that gap gets. Not smaller, wider. That's backwards. That is not how science is supposed to work. Better measurements are supposed to erase disagreements, not deepen them. Astronomers call it the Hubble Tension, and it will not go away. The first instinct, the obvious explanation, was simple. Somebody's measuring wrong. Check the equipment, check the math, recalibrate. So they did, over and over. Then the James Webb Space Telescope launched, built specifically to settle this once and for all, with cleaner data than anyone had ever collected. It confirmed the tension. It did not solve it. That's the part that quietly terrifies people in this field. Because when new, better data agrees with the disagreement, you've run out of the easy answers. It's not the telescope. It's not the math. It's not human error stacked on human error. Something in our model of the universe itself is broken. And nobody at Caltech, Harvard, or NASA can tell you what. So here's the part they're afraid to say out loud. If both measurements are correct, and the evidence increasingly says they are, then our standard model of the cosmos, the one taught in every textbook, is incomplete, missing something. Some physicists think it means dark energy isn't constant at all, that the invisible force pushing the universe apart has been changing its strength across billions of years, quietly rewriting the expansion rate as it goes. Others think there's an undiscovered particle from the universe's first fraction of a second, an early burst of repulsive energy strong enough to throw off every calculation made since. A few, more radical, wonder if we're sitting inside an enormous cosmic void, a region emptier than average, which would make our local expansion look faster than it really is everywhere else. Every single one of those explanations breaks something we thought was settled. Every one requires new physics nobody has directly observed. And here's the strange part. The tension shouldn't even be possible under the current model. It isn't supposed to exist at all. And yet it's sitting right there in the data, refusing to blink. If it's real, the consequences don't stay small. The age of the universe, the size of the observable universe, the timeline of every star, galaxy, and planet ever calculated, all of it rests on this one number. Get it wrong, and you don't just get one measurement wrong. You get the whole map wrong. And it reaches further than telescopes and textbooks. It reaches into how the universe ends, whether it expands forever, tears itself apart, or something we don't have a name for yet. Right now, our entire model of the cosmos is built on a number that cannot agree with itself. Physicists have run the tests. They've built better instruments. They've waited for the tension to fade with time. Instead, it's still growing. So what happens when the universe itself stops making sense with the rules we wrote for it? Nobody at NASA, Harvard, or Caltech will say for certain. What do you think is hiding in that gap? Tell me below.